Okay, so this is our last topic. When we were talking about concurrency, it's basically about allowing multiple transactions to execute at the same time. And you worry about whether people can read and write in the right way and so on. So that's all part of transaction management. But there's a separate problem that is different than this, but equally important, that has to do with durability. Okay? So the idea of durability is that when you finish a transaction, I want to make sure that your data is not lost. So the most important thing we care about is do not lose data. And I also care about not having inconsistencies. So I want to be able to roll back aborted transactions correctly. Okay. Now what that all means, we are going to talk about slowly. So now this is a few things here. Follow with me and make sure you understand these basic idea, right? So first of all, it's not an assumption, but it's the reality, right? Data is stored on disk. And we are going to assume that data is safe on disk. It's not like, Game of Thrones, that it will later be killed on disk as well. So, if it's on disk, you assume it's stable, okay? That means it cannot be lost, okay? So we basically call disk stable storage, which means it's not volatile, even if there is power failure. Okay? So data is our stable storage. If you succeed in putting data on disk, it's not going to be lost. There are all sorts of problems. Data may crash and so on, but they're separate, right? So you use other means to measure that, okay? But of course, to do anything with data, you have to read it into memory. So you basically, you read it in memory, you change it in memory, and there's a point until you write it back to disk, that data is volatile, right? If in fact power goes off, or somebody trips on the cable, or something happens, that data is volatile, right? So data changed in memory is volatile until it's written back. Okay. It sounds really inane, but are you with me so far? Okay. So, you have a transaction, it needs to modify many things, so it reads data pages into memory. It changes all of them. And then, just before you are done, if there's a crash, then you've lost everything, right? Because I actually did not write it back. Are you with me? This is very important, okay? You may say, oh, power failure never occurs, but, you have to make sure that that is not going to cause a problem, because it may, okay? So this is the general idea, that suppose that you basically are reading and changing things in memory. You want to make sure that you are not going to lose that data. And actually, you care most that you don't lose the data that is changed by a committed transaction. Once your transaction commits, I never want to lose the data, right? So our objective is not to lose data, okay, changed by committed transactions. So to do this, we are going to first institute something called a log. Okay? And you will see how useful log is in a second. So basically, transaction management systems use a new table we will call log. It's basically a table that is append only. You never really change old tuples, you keep adding new tuples, right? So you always add new tuples. And you keep track of what all transactions are doing in the log, right? So basically, log keeps track of what transactions are doing. And importantly, yes? No, every single thing. Everything, yes. So in fact, even recovery actions, okay? So it keeps track of everything. I don't care when you read stuff though. I care when you change stuff, right? So the things that you want to keep track of are changed data pages, okay? So you want to keep track of which transaction changed which data, okay? You keep track of commit abort actions. So you want to know which transactions were committing, which transactions were aborting, and so on. You keep track of recovery actions. Like undo for a rollback. Bless you. Okay. You also keep track of the state of the database periodically. Which is called a checkpoint, which you do periodically. Okay. So the kinds of things that you have are things about, which transactions were active, and which data pages were dirty. In this case, that means in memory, changed, but not written back. Right. We will get back to all of these in detail, but this is what a log is, right? You keep track of all of this stuff. And a very important point is that log is also created in memory. But written, bless you, fully to disk periodically. Okay? So, as with data, unless you write the log to disk, the log is also volatile, right? So we are going to have some rules about when you write data, when you write log, bless you, just so that bad things cannot happen. Okay. So any questions so far? We're going to go to all log details in a second, but let's first start with how can bad things happen. So there is basically two basic mechanisms that transactions can use. So let's go through them slowly and then see what can go wrong. Okay? So one is called force or no force, which could have been great when we did this yesterday. Let the force be with you. But anyway, so what does force mean? So let's say that if the transaction manager uses force, Force just means that I want to force updates to disk before I allow a transaction to commit, right? So if I use force, that means first, if a transaction wants to commit, okay, so the transaction declares that it wants to commit. Before I let the transaction to commit, I'm going to write all pages modified by this transaction to disk. And when they are fully done, okay, so this is the idea. This is the force step. You force, if you want to commit, I force all your changes to disk so that when I commit and say you're good, I know for sure that I have put all the data to disk. Okay? And so this is important because, if something happens, if I allow the transaction to commit, I've written the data back to disk. Okay? But if you do this incorrectly, lots of problems can occur. So first of all, let's think about what can go wrong. Okay? Let's say, for example, bad use of force. All sorts of jokes are available here. Okay, so let's say T1 has modified page 1 and page 2. So that means these two pages are in memory, and T1 wants to commit, right? So what I will do is I will basically first write page 1 to disk. Next, I will write page 2 to disk. Then I'm going to commit. You with me so far? Okay. But what can happen is, as I started my action, I wrote page 1 to disk, and at that point, there's a crash. So let's say that actually there was a crash, and I lost the change to page 2. I didn't allow T1 to commit, so that's okay, right? So T1 did not commit, but I still have a problem because page 1 is written to disk, but it has changes for a transaction that didn't commit yet, right? So I need to take whatever is in page 1 and change it back to its old state. So because T1 did not commit, right? So since T1 did not commit yet, I need to read page 1 back and undo changes. This is the recovery process, right? But how do I know what has been done to page 1? The log. But did I write the log to disk? Not clear. Well, if you don't write the log first, you will always have this problem. Okay? So in fact, we are going to have a rule that's going to be true no matter what. So this rule is going to come before here, right? This rule is called write-ahead logging. Always true. So the idea is that the log should always be ahead of data. Okay. That means before I write a data page, you. What is going on with all of you? I'm sorry? Oh, I see. Even in this stuffy room. All right, before I write data page back to disk, I will flush all of the log, including changes to P1 to disk. Okay. So anytime you have to write a data page back for whatever transaction management reason, you will always flush the log. You're never going to write a log after a certain point. If you're writing log, you write everything that's in memory because in sequential access, you can write 1 page or 10 pages probably with the same cost. It doesn't matter. So just write the log completely. Then you can write data pages back. Okay. So the log is always ahead of the data. So, and the log contains kind of a little bit. Let's give a little bit of detail. So the log has basically the following format. So it has an LSN, which is called a log sequence number, which is always incrementing. So this is always incrementing. Then you have changes. So you have things like, for example, update by transaction 1 for page X from 12 to 15, something like this. This is the page number. This is the old value. And this is the new value. So you not only store what page you changed, but what you changed, what was it before, and what is it after. But you don't actually take a whole snapshot of the whole page, right? Generally, within a data page, you change a certain part. So what you would have is you would actually have an offset, and then, let's say, start from 500, and then change 100 bytes, right? So it will always be only the part of the page that you have changed, but for simplicity, we will do it like this. And you also have things like previous LSN, which is the last previous change by this transaction. Okay. So this is what the log will actually look like. Just to see a small example. Something like this, right? So you basically have the LSN, which is always increasing, okay? And you have log entries. So this one says T2 updated page Y from 21 to 25, and this was the first thing for T2. Then T1 did page X from 12 to 15, this was the first thing. Then T2 committed, and the previous thing it did was 1234. Then T1 did page Y from 25 to 31, right? This one did 21 to 25, this is 25 to 31, and this was 1235. Then T1 committed, and the previous thing it did was this one, right? So this is basically how the log looks like. In addition to this, you also keep track of information about data pages in memory. So for each data page, remember when we talk about data pages, there is a header. In the header, you will basically store it's kind of sad. Store the LSN of the last change to that page. Right? So basically, when you write the disk page back, you also have the log sequence number of the last thing that was changed in that page. Right? So, for example, going back to this, here, if I wrote this page, when I committed T2, if I wrote this page back to this, the last thing that changed this page was 1234. So after that, it may have been changed. If I didn't write this page back yet, there may be changes in memory that are not yet written. So the page in memory will have the last change here at 1237, whereas the page on this may have 1234, right? So, the last LSN is the one that was the last change at the time I recorded it. So basically, the dirty page is all pages in memory that are changed, but not yet written to disk. So there may be changes still in memory, not written to disk, and so on. We will see the point of that. Okay, so now let's do the force correctly, right? So we don't want this happen. We don't want the case where you write pages back to disk, but you cannot figure out what happened to them. So what I'm going to do is this. Okay, I'm going to change this, and I'm going to say first write a commit record to log, and then flush the log. So first write that I'm committing this transaction. This transaction wants to commit. And then write all pages. So write the log. Now I know for a fact what this transaction has done. It's in the log. Even if it crashes after this point, I can always trace back two things. I can trace back that which pages should have been modified, and I can also trace back that the transaction wanted to commit, right? But if there is no crash, then I'm going to write all the pages to disk after the log. This is the write-ahead logging here. And when that is done, I'm going to basically allow the transaction to commit. Only then I will say, okay, you can go ahead, right? So let's talk about, first of all, what are the kinds of things that can happen, right? So first, okay. So first of all, good and the bad. The point is that if I see a commit transaction, I will know that if I actually allowed the transaction to commit, if it's no longer in memory, all of its data pages are written to disk. Okay, so it's kind of simple, because if transaction committed, then I know that it has no dirty pages. The bad, though, is that multiple transactions can actually use that data page, but I'm going to basically keep all the data in memory until it is time to commit. Okay, so as a result, I'm not using memory very well, and I'm writing a lot of pages back. What if those pages were going to be used by some other transaction, right? So it may be costly that you're writing all the pages. They could have been used by another transaction, and then when everybody is done, put it back, right? So So good. It's a simple method for concurrency. If I don't write until you're about to commit, and if I allow you to commit, I know for sure that there is no bad data. But it is a lot of cost to be writing all these pages unless you know for sure that no other transaction is going to use it. So force in this case can be bad. Okay? So let's talk about steal. Remember that when we're talking about query costs, I basically keep telling you, n is equal 10, n is equal 101, right? So anytime I allocate memory to a transaction, right, that transaction can go faster, right? But that means though those 101 pages are just blocked for this one transaction until that transaction is done, nobody can use this amount, right? So that means if you have 10 transactions, each have to have their own slice of the memory, and so you can give them smaller slices, right? Because they are using that memory exclusively. If you allow them to share the same memory block, what does that mean? That means I actually have to, if I modify that whatever page was in that block, I have to write it back to disk so that that block can be used by somebody else. But the next transaction, if it has more memory, it can go faster, right? You saw how sort is so much faster if you give it more memory. So if you allow transactions to steal memory blocks from each other, they can go faster, right? So this is the general idea. So if you have steal, so I guess it's easier to talk about what is no steal. So no steal means that all transactions have their own dedicated memory block. Well, then that means you can have less because you're slicing it to more people. But the good thing is that now all the data that you modify, you can keep in memory until your transaction completes. So that means you can keep in memory all data pages until you commit. So you never have to write dirty data back to disk. Once you start to write this page, you know for sure that that's for a transaction that was about to commit. You with me so far? Right? So, so no steal is kind of nice because recovery is very, very simple, right? So when you have a crash, you never have to check if something was written, then it has to be undone because it will only be for transactions that are committed or were committing. But, so good means easier recovery. Because never dirty, uncommitted data on disk. But the bad is that you're basically able to use memory less efficiently. So, just for your purposes, I'm going to write what steal is as well, so we understand. So this was no steal. So steal means steal means that transactions can actually steal memory blocks from each other. if that memory block happens to contain a modified page, you have to write it back to disk. So if the memory block contained a dirty page, remember, a dirty page that is changed by an uncommitted transaction, right? So it's changed by uncommitted transaction. Then you have to first write the log. Because of write-ahead logging, right? Then write the data page, and then release the memory to other transactions. Okay? So basically, when we are looking at recovery, it all depends on whether you have force or steal. Because of that, your assumptions are going to change, right? So this is where we're going to talk about different recovery algorithms. So any questions about force or steal? So the idea of steal is that you basically do memory management, and generally you actually don't even do it by the database. The operating system will write things as, least recently used, most recently used. It will change it back and give the memory between different transactions. But that means, as a result of that, the data pages written may actually be dirty, right? So this is where we have to define what our recovery algorithm is, right? But it will pretty much depend on what is being used, right? So this will depend on steal versus force, if they are used or not, right? So basically, the idea is that if you use no steal and you use force, right? So it means that you don't write anything until, so you keep everything in memory, no steal, right? So everything is kept in memory until it is time for the transaction to commit. At that point, you write the log, you put a commit record, you flush the log, then you start writing data pages. So in this case, recovery is kind of simple. And it only includes redos. Right? But it happens that this is the least efficient way of doing transaction management, because you are not using memory blocks well, you are writing data pages so that you may have many more scans than needed. Generally, what we want is this, that you allow both no force and allow steal. That means you don't wait until the transaction ends to write pages so you can share memory. And then when a transaction ends, you don't actually necessarily force all the data pages, right? So how does no force work? Well, in no force, you basically commit transaction, right? So let's write that one too. So let's make sure that we understand all of these. So no force means that if transaction wants to commit, you write a commit record on log. Then you flush the log the list. Then allow the transaction to commit. all I care is that the log is written to disk. It is true that the data may have been modified by the transaction, and those pages are still in memory, but based on the operating system, those will eventually be written back to disk, right? But I'm not going to force them, so that means other transactions can make use of those pages that are already in memory, and when they need the space, they will be written back, right? So this is kind of the ideal scenario is no force plus steal, right? Okay? All right. There we go. Let's talk about recovery. Okay. So something catastrophic happened. Okay. Well, let's see. Should we do recovery? Or should we do rollback? Let's do rollback first, and then we'll do recovery. All right. So let's say rollback. You suddenly realize a transaction has to abort, right? So let's say transaction T1 aborts. Okay. So if transaction T1 aborts, I have to first undo everything transaction 1 did, right? So if I use no steal, there's nothing to do, right? Because I actually have not changed any of the data pages in disk, right? So if no steal, then only change pages in memory. Okay. So you basically go through the log. So the log will have data entries for T1. So this is all the things that T1 did. And there are many other things here, but I don't care about them. And basically, when I have a board, it has a log sequence number. Let's say this is 5001, and the previous one was 4993. So this is 4993. The previous one was 4885. So this is 4885. And then this is nothing, right? So I decided to abort T. And the previous thing it did was 4993. So now I have to travel back in my log and says, okay, go to 4993. And this was a page of T1, change of page of T2, page 2, from 21 to 25, change 25 back to 21. Since if there is no steal, it's already in memory, I can do this easily. If there is steal, then I have to check. If it is not in dirty page table, that means it's been written to disk. So I have to read it back from disk. And then I have to change it back. Either way, I am going to write a new log that says that I am undoing 4993. Okay. And my previous LSN for this one is going to be now 4885. Now I'm going to go to 4885, that's about page 1. Again, if no steal is used, I can change it in memory. If steal is used, then I may have to read it back if it is not in dirty page, bring it back to memory, and I'm going to do undo of 4885. Okay. There is nothing previous to do, and I'm actually going to write that T1 is ended. Okay. So the distinction is that based on steal or no steal, I may actually have to read these pages back. Now there's a few things here that are hidden from you at this point. One thing is that I am just following these without really looking at other transactions, right? That's possible because I have allowed a concurrency control that doesn't require that I basically cascadingly abort other transactions. Because I'm making sure that nobody reads each other's bad data, right? Because if I change page 1 here, and somebody did something to page 1, I have to abort that transaction too, right? So this is kind of a complicated problem. So we are simplifying to make sure that this is not needed, no need for cascading aborts because nobody is reading somebody's dirty data. Remember that there was a thing that, there was a name for this, right? In SQL, you actually have a thing called read committed isolation, right? If you always have read committed, then you never have to really check if somebody has read your dirty data, right? So because of that, I can just go independently and undo things that this transaction did. Otherwise, I have to scan through here to see if anybody else has touched page 1. But we are going to assume that's not possible, but there's algorithms to handle that too. So this is the idea of a rollback, because I have everything in memory. When something happens and there is a crash, things are a little different. Because when there's a crash, I don't know what happened. I don't know what was happening at the time, because I've lost two things, right? I have lost all log that was in memory, all dirty pages, and any transaction state for transactions that have not been completed yet. So I basically have a complete amnesia of what was happening. I've lost all of the state. So the only thing that I know is what is on disk. So I'm going to now retrace my steps by looking what was recorded on disk and then start recovery from that. So basically the idea is that I have to go back to disk, read the log, and recover my state. So I'm going to take, let's say for simplicity, I'm going to start reading the log from the first record all the way to the forward. I'm going to start from the beginning of time and trace my steps to come to the point before the crash. So I'm going to read the log and then figure out what was happening. So we said that the log contains many different things, right? So it will basically have it will have many records. Okay. And it will be things like update T1, update T1, update T1, update T2, update T3. So let's say T1 changed page 1 from 5 to 6, T2 changed page 2 from 8 to 10, then T1 changed page 3 from 12 to 13, then this one is committed, then T3 read page 2, now it's a committed value, change it from 10 to 12, then T1 changed, and I'm going to get rid of this one here, okay? So then T1 changed page 4 from 8 to 15. Then T1, change page 3 again, from 13 to 15. Okay, now we can put the previous LSN for these. So this is 1001, this is 1002, this is nothing, this is 1003, and this is 1006. All right, this actually makes no sense. This is a commit record. Okay. All right. So this is what I found in the log. Okay. So basically, it tells me that this is what I've written to log so far. Okay. Based on what I find, okay, let's try to figure out what can we say. So what can we say about transaction 3? If this is what I find in the log, what do I know about transaction 3? Is transaction 3 committed? No, because I will not commit until I write a commit record and flush that to disk, right? So we know for sure that T3 did not commit, right? So this is called the analysis phase, right? So I'm doing analysis in the forward motion here, okay? One thing I know for sure is T3 did not commit. Okay, so that means I need to abort it. Okay, so what do I know about T1 and T2? They are both committed, but what do I know about the pages that they have written? Have they been flushed to disk? Do I know? Even if I'm using force, is it guaranteed that all those pages have been written to disk? I don't, right? So I need to make sure that, so T1 did not commit, it must be aborted. So if steal is used, I need to read data pages back and undo. Read pages back and undo. Okay. In the other way, T1 and T2 have committed, but if I don't use force, if no force is used, then I must read pages and redo the changes to make sure that they are actually recorded, because there is no guarantee that the changes are actually recorded. Okay? So this is basically the idea of recovery. The idea of recovery is that you first analyze to understand which state you are in. Then you decide some transaction must be aborted because they were not completed. Then you have to undo the changes for them. And if you do not use steal, then you have to read those pages back. For the committed transactions, if no force is used, then you actually have to make sure that you read those pages and you redo the changes. So basically, you're going to use the log for both undo and redo. So on Monday, what I'm going to do is I'm going to show you an algorithm that achieves both. And if you use one or the other, you can actually skip some steps, and we will talk about that. And then I am happy to answer any questions and review any material in the remaining time. So that will probably take half the class to do the algorithm, and then we'll be done. So I'll see you on Monday.